Right now, in the space between these words, light is landing on your eyes. It has just finished a journey of 8 minutes across roughly 150 million kilometers of empty space. And yet, more than a century after Einstein, physicists still cannot give you one simple, final answer to a deceptively simple question. Is light a wave, or is it a particle? Tonight, we are going to sit with that paradox until it stops feeling like a contradiction and starts feeling like a doorway. Hello, and welcome to Somniora Mind. I'm glad you're here. Before we begin, if a quiet place like this one has ever helped you drift off, the simplest way to support it is to subscribe, or to leave a comment, or just to tap that little like button. It costs you nothing but a second, and it genuinely helps this space keep existing. Now, let yourself sink into the mattress, let your shoulders drop, and let's begin. Here is what we'll uncover before the night is through. We'll find out why the sky above you is blue, and why that answer is stranger than almost anyone expects. We'll trace a beam of starlight back across time and discover that some of the light reaching your eyes tonight is older than every civilization that has ever existed on Earth. And near the end, we'll sit for a while with a question that unsettled Einstein himself. What does it mean for two particles of light to seem to know about each other across the width of a galaxy? Here is a number to start with. Every single second, the sun converts about 4 million tons of its own mass directly into light. Not fuel, not smoke. Mass itself, disappearing into pure radiance, streaming outward in every direction, most of it vanishing uselessly into the dark, and a tiny, tiny fraction of it landing 8 minutes later on a windowsill, a leaf, an eyelid. Light is so woven into ordinary life that it becomes almost invisible to notice. It slides through a window in the early morning and stretches across a wall. It catches the rim of a glass of water. It slips into a mirror and comes back as your own face. It turns leaves green and clouds white and evening skies the color of a bruised peach. It carries pictures into cameras and information down glass fibers thinner than a hair, and it carries warmth across the entire distance from the sun to your skin. Light is so familiar that we take it for granted, and so strange that it has occupied some of the sharpest minds our species has ever produced. Think about a lit screen glowing on its own, a red sweater, which absorbs some wavelengths and throws back others, a clean window, which lets some light straight through while bouncing part of it back at you, a shadow, which is really just a patch of world where light has been quietly turned away. Every single thing you have ever seen is the result of some combination of light being made, moving, bouncing, bending, scattering, being swallowed, and finally being caught by something built to notice it. And that catching matters more than people usually realize. Light itself is not the same thing as seeing. Light is a physical event, a ripple moving through space. Vision is your body's biological reaction to a narrow sliver of that event. Human eyes only detect a thin band of what's called the electromagnetic spectrum, wavelengths roughly between 400 and 700 nanometers. A nanometer is a billionth of a meter, so we are talking about slices of space thinner than you could ever picture. And still, that thin band is the entire visible universe as far as your eyes are concerned. But that band is only a sliver of something much larger. Stretch out past red, past what your eyes can register, and you move into infrared, then microwaves, then radio waves, wavelengths that can stretch longer than a building, longer than a city block. Stretch the other direction, past violet, and you move into ultraviolet, then X-rays, then gamma rays, wavelengths so small they can slip between the atoms of your own skin. These aren't different substances. A radio wave and a beam of visible light are made of the same underlying stuff, differing only in wavelength and energy. The reason they feel like different phenomena is simply that they interact with matter differently. Your eyes respond to visible light but ignore radio waves entirely. Water molecules quietly absorb certain microwave frequencies, which is the entire principle behind a microwave oven. Ultraviolet light can trigger chemical changes in skin cells. X-rays slide easily through soft tissue but catch on bone. Gamma rays carry enough punch to knock electrons clean off atoms. Nature never drew hard lines between these categories. We did. It's a little like naming regions on a single, continuous coastline. The land doesn't change just because we've decided to call one stretch the north and another the south. One of the strangest features of light is that it doesn't need anything to travel through. Sound needs air or water or some material to carry it along. But light crosses the total emptiness of space just fine, arriving from the sun in a little over 8 minutes, arriving from the next nearest star system after more than 4 years, arriving from the most distant galaxies after literally billions of years of uninterrupted travel. This is why light is one of science's most trusted messengers. We will never scoop up a sample from a star 1,000 light years away. We will never fly a probe to a galaxy on the far edge of the observable universe. But we can study its light, and from that light alone, infer its temperature, its chemical makeup, its motion, even the presence of matter we cannot otherwise detect at all. Light also carries energy, which is the reason the ground under your feet warms in the sun, the reason solar panels can turn afternoon light into electricity, the reason plants can build sugar out of nothing but air, water, and sunlight. Inside a leaf, specialized pigment molecules, chlorophyll chief among them, absorb particular wavelengths of light, mostly red and blue, which is part of why leaves reflect the green they don't use and appear that familiar color to us, and use that captured energy to rearrange simple, low-energy molecules into sugar, a stable little packet of stored sunlight that will later feed the plant, and eventually, nearly every animal on the food chain above it, including you. Almost every meal you have ever eaten is, if you trace it back far enough, sunlight, caught by a leaf sometime in the past, and patiently passed hand to hand until it reached your plate. And in one of the more counterintuitive facts in all of physics, light also carries momentum, despite having no mass whatsoever. This sounds like it shouldn't be possible. Momentum, in ordinary experience, comes from mass and motion. But photons, the quantum particles of light, don't play by that rule. They always move at the speed of light, and they can still push on the things they strike. The push from ordinary daylight is unbelievably small, but it is measurable, and engineers have proposed entire spacecraft, called solar sails, that would drift outward through the solar system on nothing but the gentle, patient pressure of sunlight. For centuries, the deepest argument in physics was whether light was fundamentally a stream of particles or a wave rippling through space. Isaac Newton leaned toward particles, imagining light as a stream of tiny corpuscles fired outward from a source in perfectly straight lines, an idea that fit beautifully with the clean, sharp geometry of shadows and mirrors. Christian Huygens, working around the very same time, argued instead for a wave, something rippling outward through space the way sound ripples through air. Newton's enormous scientific reputation carried his corpuscular theory forward for the better part of a century, largely by force of authority as much as evidence. Thomas Young's experiments seemed to settle it in favor of waves. James Clerk Maxwell then showed that light was, in fact, an electromagnetic wave. And then Max Planck and Albert Einstein came along and showed that light also exchanges its energy in discrete, particle-like packets. None of these thinkers were simply wrong. Each one had captured a real piece of something larger than any single description could hold. Tonight, we're going to walk through all of those pieces, one at a time, slowly, the way you might walk through a house at night with a single candle, letting each room reveal itself before moving to the next. Let's start at the beginning, not of physics, but of curiosity. Long before anyone understood electromagnetic fields or photons, people had already noticed that light seemed to travel in very orderly ways. Shadows had crisp edges. Mirrors gave back recognizable faces. A narrow crack in a wall could throw a bright, clean patch of light onto the opposite side of a room. These were the first clues that light moved along something like straight paths that could be studied with lines and angles, the same way a surveyor studies a field. The earliest theories of vision didn't all agree on the most basic point, which direction the light was even traveling. Some ancient Greek thinkers imagined that sight worked by something traveling outward from the eye and touching the world, almost like a hand reaching out in the dark. It sounds strange to us now, but it made a certain intuitive sense. Looking at something does feel active, doesn't it? Like your attention is reaching toward it. Other thinkers believed objects released faint copies of themselves that traveled inward to the eye. The debate simply couldn't settle. Did the eye send something out, or did the world send something in? Euclid, writing in ancient Greece, built an elegant geometry of vision using straight lines radiating from the eye. He had the direction backwards, but the geometry itself, the careful reasoning about angles and distances and reflections, turned out to be genuinely useful and would outlive his mistaken assumption by well over 1,000 years. Centuries later, the astronomer Ptolemy extended this geometric approach, carefully measuring how light bent when it passed from air into water, though he too still assumed the eye was somehow sending rays outward. The real correction came from a scholar working in the Islamic Golden Age, a mathematician and physicist named Ibn al-Haytham, known in medieval Europe as Al-Hazen. Working in the late 10th and early 11th centuries, he proposed something that seems obvious to us now, but was genuinely revolutionary at the time. Light travels from a source, bounces off an object, and only then enters the eye. The eye doesn't reach out, it receives. He laid this out in his monumental work, the Book of Optics, and he didn't just theorize, he tested. He built a darkened room with a single small opening in one wall, and watched as light from the outside world pass through that opening and painted an upside-down image on the far wall. This device, essentially the ancestor of the pinhole camera, proved something important. Light doesn't wander freely from point to point. It travels along straight paths, and when you narrow those paths down to a single small opening, you can trace exactly where each ray of light has been. This is the foundation of what we now call geometric optics, the physics of straight rays, mirrors, and lenses. A shadow forms because an object blocks the straight-line paths of light from a source. A solar eclipse happens because the moon blocks sunlight from reaching part of the Earth. A lunar eclipse happens because the moon passes through the Earth's own shadow. And the sharpness of any shadow depends on the size of the light source itself. A small, distant source, like a candle across a room, produces crisp edges. A big source, like the sun, produces a darker center called the umbra, surrounded by a softer, lighter edge called the penumbra, where the light source is only partly blocked. Reflection follows its own beautifully simple rule. The angle at which light arrives at a smooth surface equals the angle at which it leaves, both measured from an imaginary line perpendicular to the surface. This is why a still lake gives back a perfect, upside-down copy of the trees along its edge, and why a flat mirror shows you a face that seems to sit just as far behind the glass as you are standing in front of it. Most surfaces, though, aren't smooth enough to behave like mirrors. A painted wall might feel flat to your hand, but under a microscope, it's a landscape of tiny bumps and ridges, scattering incoming light in every direction. This is called diffuse reflection, and it's the entire reason you can see an ordinary object from more than one angle at once. A polished surface, by contrast, keeps that reflected light organized enough to form a clean image, which is called specular reflection. When light passes from one transparent material into another, say, from air into water, it doesn't just slow down politely and keep going straight. It bends. This is refraction, and it's why a straw in a glass of water looks broken at the surface, and why a swimming pool always looks shallower than it really is. The amount of bending depends on something called the refractive index, a number that describes how strongly a material slows the wave's phase compared to empty space. Ordinary glass has a refractive index of about 1.5. Water sits around 1.33. Light bends more strongly when it crosses into a material with a higher refractive index, and less strongly moving the other way. There's a beautifully strange principle buried underneath all of this, first proposed by the French mathematician Pierre de Fermat. Fermat's principle says that light always follows the path that takes the least time between 2 points, not necessarily the shortest distance. Picture a lifeguard running along a beach to save someone struggling in the water. The fastest route isn't a straight line, because running on sand is faster than swimming. The smartest lifeguard runs at an angle, covering more ground on sand and less in the water, minimizing total time rather than total distance. Light does exactly this, instinctively, every single time it crosses a boundary between materials, and this single elegant principle can be used to derive both the law of reflection and the law of refraction from scratch. Different wavelengths bend by slightly different amounts inside the same material, a phenomenon called dispersion, and it's the reason a prism can take a single beam of white sunlight and spread it into a full ribbon of color. It's also the reason a diamond sparkles the way it does, redirecting light through dozens of internal bounces, splitting wavelengths apart, and sending flashes of separated color back toward your eye. A skilled cutter shapes the many facets of a diamond specifically to maximize this effect, angling each surface so that as much light as possible enters, bounces internally several times through total internal reflection, and finally exits back toward the viewer's eye already separated, at least partially, into its component colors. That's why a well-cut diamond seems to flash tiny sparks of red, blue, and green as it turns in the light, even though the stone itself and the plain sunlight falling on it are both, technically, colorless. It's an extraordinarily elaborate use of geometry for what is, underneath all the sparkle, just a small piece of very orderly carbon. There's one more trick refraction can play, and it might be the most useful one in the modern world. When light inside a dense material like glass tries to exit into a less dense material like air at a steep enough angle, something unusual happens. Instead of bending out, it reflects entirely back inward, as if the boundary had suddenly turned into a mirror. This is called total internal reflection, and it's the entire principle behind fiber optic cables. A hair-thin strand of glass can trap light inside itself, bouncing it along a slightly curving path for hundreds of kilometers without it ever escaping, carrying phone calls, videos, and this very sentence somewhere through some undersea cable right now. Modern fiber optic networks push this idea even further than simply trapping one signal inside one strand of glass. Different wavelengths of light can travel down the very same fiber simultaneously, each one carrying its own separate stream of information without interfering with the others, a technique that lets a single hair-thin cable carry an almost unimaginable amount of data at once. Entire cities' worth of conversations, video calls, and quiet late-night video essays like this one, all riding together, invisibly, at the speed light allows inside glass. Bundles of thousands of these fibers are also used in medical endoscopes, threading illumination down into the body and carrying an image back out again, letting a physician see clearly into spaces that would otherwise be completely inaccessible without surgery. It's a strange thought, if you sit with it. The same total internal reflection that traps a wandering beam of light inside a diamond is, in a slightly more organized form, letting a doctor look quietly inside a living human body, or letting this very sentence travel across an ocean floor to reach wherever you happen to be resting right now. Curved surfaces put refraction to work, forming images. A converging lens, thicker in the middle, bends parallel rays inward to a single focal point. A diverging lens does the opposite, spreading rays outward as though they came from a point in front of the lens. Every camera, telescope, microscope, and pair of glasses on the planet is built from careful combinations of these two simple shapes, along with the very same eye you're using to imagine all of this right now. A telescope, at its simplest, uses one lens or mirror to gather a wide cone of faint light and bend it down to a small, bright focus, and a second lens to magnify that focused image for your eye. A larger telescope isn't just about magnification, it's fundamentally about collecting more photons from a dim, distant source, which is why observatories keep building mirrors that are larger and larger and larger still. A microscope works in reverse, taking a tiny, close object and spreading its image out to a size your eye can actually resolve. And your own eyes, when they don't quite focus properly, can be corrected using exactly the same principles. If your eyeball is slightly too long, or your cornea curves a little too steeply, light focuses just in front of your retina instead of directly on it, blurring distant objects, a condition called nearsightedness, correctable with a diverging lens that spreads the light out just enough before it enters the eye. If your eyeball is slightly too short, light would focus just behind the retina if it could, blurring nearby objects instead, a condition called farsightedness, correctable with a converging lens that adds a little extra bending before the light ever reaches your cornea. Refraction doesn't only happen at hard boundaries, like the edge of a raindrop or a pane of glass. It can also happen gradually, continuously, through air itself, whenever that air has different temperatures at different heights. This is what produces a mirage, that shimmering illusion of water pooling on a hot road on a summer afternoon. Very hot air near the asphalt has a slightly different refractive index than the cooler air above it, and light from the sky bends gradually as it passes through these shifting layers, curving upward into your eyes in a way that your brain, trusting its lifetime of experience with straight-line light, misinterprets as a reflection off a wet surface. The same gradual bending happens every single sunset. Earth's atmosphere grows denser closer to the ground, so light from the sun curves very slightly as it passes through the thickening air, which means the sun stays visible for a short while after it has technically already dropped below the true geometric horizon. In a very real sense, every sunset you have ever watched finished a little later than it should have, purely because the atmosphere gently lied to you about where the sun actually was. There's a further, quieter beauty to atmospheric refraction that most people never notice, simply because it happens in the deepening dusk, once most eyes are indoors. After the sun has fully set, the upper atmosphere can remain lit for a while, even as the ground below sinks into shadow. Look toward the point directly opposite the sunset, and you may catch a dim, blue-gray band rising slowly along the horizon. That's the Earth's own shadow, projected outward onto its own sky. Just above it, a soft pink glow sometimes appears, poetically named the Belt of Venus, though the planet itself has nothing to do with it. It's simply reddened sunlight, still grazing the upper atmosphere, illuminating the air just above the rising edge of our own planet's shadow. It's a display most people walk right past every single evening, without ever once looking up to notice their own world's shadow, quietly climbing the sky behind them. Now let's talk about speed, because light's speed turns out to be one of the strangest facts in the entire universe. In the 19th century, physicists believed that if light was a wave, it needed something to wave through, some invisible medium filling all of space, which they called the luminiferous ether. In 1887, two American physicists, Albert Michelson and Edward Morley, built an extraordinarily sensitive instrument to detect the Earth's motion through this supposed ether. They split a beam of light into two paths at right angles, bounced both beams back, and recombined them, expecting to see a shift caused by the Earth's movement through the ether. They found nothing. No shift at all. The ether, as far as their instrument could tell, simply wasn't there. Then, in 1905, a young patent clerk named Albert Einstein proposed something radical to explain this null result. What if the speed of light in a vacuum is simply the same for every observer, no matter how fast they themselves are moving? This breaks every intuition we have about ordinary speed. If you're standing beside a road and a car drives past while someone inside throws a ball forward, you'd measure the ball's speed as the car's speed plus the throw's speed. Light refuses to behave that way. Someone racing toward a beam of light and someone racing away from it will both measure the exact same speed for that light. Nature, it turns out, preserves this constant speed by bending something else instead, space and time themselves. Moving clocks run slower, an effect called time dilation. Moving objects shrink slightly along their direction of motion, an effect called length contraction. And two events that look simultaneous to one observer might not be simultaneous to another observer moving differently. These aren't illusions caused by signal delays or bad clocks. They are real, physical features of how space and time are woven together. And the speed of light is the thread holding that fabric in shape. Because light has a finite speed, and because nothing can travel faster than it, every single thing you have ever looked at is, in a very real sense, already history by the time you see it. The moon you see is the moon as it looked about 1¼ seconds ago. The sun you feel warming your skin is the sun as it looked 8 minutes ago. The nearest large galaxy beyond our own, visible faintly on a clear dark night, is showing you light that left it over 2 million years before the first cities were ever built on Earth. Looking up at the night sky isn't just looking outward through space. It's looking backward through time, layer after layer, star by star, all the way to the edge of what light has had time to reach us from since the universe began. And that edge is a real, physical thing, not just a poetic phrase. Roughly 13.8 billion years ago, the universe was so hot and so dense that light couldn't travel freely at all. It was constantly scattered, absorbed, and re-emitted by a thick fog of charged particles, the way light struggles to travel far inside a dense cloud. About 380,000 years after the beginning, the universe finally cooled enough for atoms to form properly, and that ancient fog cleared, all at once, everywhere, letting light travel freely for the very first time in the universe's entire existence. That first free light is still out there, still arriving, stretched by the ongoing expansion of space itself into faint microwave wavelengths our eyes could never see, but our instruments can measure with extraordinary precision. Astronomers call it the cosmic microwave background, and in a very real sense, it is the oldest light in existence, a faint, cooling afterglow of the birth of everything, still gently, quietly arriving from every direction in the sky, right now, tonight, while you lie here listening. So how does light come into being in the first place, before it ever gets the chance to travel anywhere? At the broadest level, electromagnetic radiation is produced whenever charged particles accelerate, or whenever a quantum system drops from a higher energy state to a lower one. One of the most familiar sources is simple heat. Anything warmer than absolute zero has particles jittering around inside it, atoms vibrating, electrons shifting, and that restless motion radiates electromagnetic energy outward. This is called thermal radiation, and it explains why a piece of metal, heated enough, begins to glow, first a dull red, then orange, then yellow, then eventually a blinding blue-white as it gets hotter and hotter. The hotter something gets, the shorter the wavelength of its peak emission, a relationship called Wien's displacement law, which is why cooler stars in the night sky look reddish and hotter stars look icy blue. It's a small, quiet irony of the universe that among stars, red means cooler and blue means hotter, the exact opposite of how we tend to describe temperature in daily conversation. There's a second law tucked inside this same idea, named after the physicists Joseph Stephan and Ludwig Boltzmann, and it describes something almost startling. The total energy radiated by a hot object doesn't just creep upward as temperature rises, it explodes upward in proportion to the fourth power of the object's absolute temperature. Double an object's temperature, and it doesn't radiate twice as much energy. It radiates 16 times as much. This is part of why the sun, at roughly 5,500 degrees Celsius on its visible surface, is so overwhelmingly brighter than a stovetop element glowing orange at a few hundred degrees. The difference in temperature sounds significant, but almost manageable. The difference in brightness is anything but. Physicists describe an idealized version of this kind of emitter as a black body, meaning a perfect absorber and a perfect emitter, radiating a spectrum shaped purely by its temperature and nothing else. No color, no texture, no material properties of its own. No real object is a perfect black body, but stars come remarkably close, which is part of why their light tells us so much, so precisely, about their internal furnace. Light is also produced when electrons inside atoms drop from a higher, more energetic state down to a lower one, releasing the difference as a single photon. Because every chemical element has its own unique arrangement of these energy levels, every element produces its own particular signature of colors. This is how a neon sign glows its familiar reddish orange, how sodium street lamps cast that warm yellow glow, and how astronomers, without ever touching a distant star, can determine exactly which elements exist inside it, just by carefully reading the colors in its light. Then there are LEDs, light-emitting diodes, which produce light through a process called electroluminescence, electrons and their absent counterparts, called holes, colliding inside a semiconductor and releasing photons as they recombine. And there are lasers, which use a far more organized process called stimulated emission. Inside a laser, one photon encourages an already excited atom to release a second photon that matches it exactly in frequency, phase, and direction, and that second photon encourages a third, and so on, building an avalanche of perfectly synchronized light, bouncing between two mirrors until a narrow, brilliant, coherent beam escapes through one end. Different sources give you very different kinds of light. Heat gives you a broad, messy spread of many wavelengths in every direction. A gas lamp gives you sharp, specific spectral lines. An LED gives you a controlled, efficient slice of the spectrum. A laser gives you something almost unnaturally orderly, waves marching together in lockstep. And the same underlying pattern runs through all of it, in a candle flame, a screen, a lightning bolt, or the heart of a star. Charged matter shifts, energy rearranges itself, and the electromagnetic field carries a piece of that energy away as light. Once light exists and starts moving, its story becomes about what it meets along the way. A beam crossing empty space can travel forever undisturbed. But the moment it touches matter, several things can happen at once. It might be absorbed, soaked into the material, and converted into heat or some other form of energy. It might be transmitted straight through. It might be reflected back the way it came. Or it might be scattered, redirected in many different directions at once. Most real materials do a combination of all four in different proportions for different wavelengths. Absorption happens when a material has some available way to accept the energy a photon is carrying, maybe by kicking an electron up into a higher energy state, maybe by making a molecule vibrate or spin faster. This selectivity is why transparency is never a truly universal property. A pane of ordinary glass looks perfectly clear to your eyes, letting most visible light sail right through. And yet that very same glass is quite good at absorbing ultraviolet light, which is exactly why you can get sunburned sitting in direct sun, but not through a closed car window. Reflection, at the microscopic level, isn't really like a ball bouncing off a rigid wall. The electric field of the incoming light shakes the electrons at the surface of the material, and those shaken electrons generate a wave of their own, radiating back outward. Metals are especially good at this because they're full of loose, mobile electrons that respond eagerly to any incoming field. This is also why different metals have different colors when polished. Gold reflects red and yellow wavelengths beautifully, but absorbs more of the blue, giving it that warm golden glow. Silver reflects almost everything roughly equally, which is why it looks so brilliantly, neutrally bright. Scattering redirects light without necessarily swallowing all its energy. It happens whenever light meets something smaller than or comparable in size to its own wavelength, whether that's a molecule of air, a tiny water droplet, or an irregularity buried inside a material. A sheet of clear glass barely scatters light at all, which is why you can see cleanly through it. Frosted glass is made of nearly the same material, but its rough surface scatters the light in every direction, so it still lets brightness through while blurring away any clear image. This is the real difference between something transparent and something merely translucent. And color, it turns out, doesn't live inside objects the way we tend to assume. A green leaf isn't green because it contains greenness. It's green because the pigments inside it absorb red and blue wavelengths strongly while reflecting green back at you. A red filter doesn't add red to white light passing through it. It simply blocks most of the wavelengths that aren't red and lets the rest through. Even a dark shirt getting warmer in the sun is a straightforward story of absorption. Dark materials soak up more visible and infrared light, converting it into heat, which is why black fabric always runs hotter under the same sun than white fabric does. This brings us to the deeper question of where color actually comes from, because the physical world, strictly speaking, has no color of its own. Electromagnetic radiation carries wavelengths, and wavelengths alone. Color is something your nervous system builds, using those wavelengths as raw material. Isaac Newton demonstrated this beautifully in the 17th century, letting a beam of sunlight pass through a glass prism in a darkened room and watching it spread into a full ribbon, red through orange, yellow, green, blue, violet. Some people at the time assumed the prism itself was somehow adding color to plain white light. Newton tested this by isolating a single color from the spread and passing it through a second prism. It didn't split further. It bent again at a slightly different angle, but stayed exactly the color it already was. Then he used a second prism in reverse to recombine the separated colors and watched them merge back into ordinary white light. The prism wasn't creating color. White sunlight had always secretly contained the entire rainbow, all mixed together, and the prism was simply sorting it out by wavelength, because glass bends different wavelengths by very slightly different amounts. Here's something worth sitting with for a moment. There is no physical line where orange stops and yellow begins. The visible spectrum is smooth and continuous. Nature never divided it into neat little boxes. We did that, the same way we draw borders on a map, even though the actual landscape flows seamlessly from one region into the next. Your eyes detect color using 3 types of cone cells in the retina, loosely tuned to short, medium, and long wavelengths, roughly corresponding to blue, green, and red. But no single wavelength triggers only one type of cone. Every color you've ever seen is really a pattern, a particular ratio of activity across all 3 cone types at once, which your brain then interprets as a single sensation. This is why 2 completely different mixtures of wavelengths can sometimes trigger the exact same pattern of cone activity and look identical to you, a phenomenon called metamerism. It's the entire reason a screen can convincingly fake millions of colors using only tiny red, green, and blue lights combined in different intensities. Purple, in fact, doesn't correspond to any single wavelength in the rainbow at all. It's a construction your brain builds by activating your short wavelength and long wavelength cones together, without much in the middle. In a strange sense, purple is one of the more purely mental colors there is, born entirely from the particular architecture of your own eyes. Different sources of light also carry entirely different mixtures of wavelengths, even when they look roughly similar to your eye at first glance. Sunlight at noon carries a broad, fairly even spread across the whole visible spectrum, which is why it's often used as a reference point for judging how true other colors look. An old-fashioned incandescent bulb glows using thermal radiation and leans heavily toward the longer, warmer wavelengths, which is why photographs taken under 1 often have that familiar yellowish-orange cast and less corrected. A fluorescent tube produces its light very differently, through a handful of sharp, separated spectral peaks rather than one smooth curve, which is part of why colors can look subtly, unsettlingly off under certain fluorescent lighting, even when the overall brightness looks perfectly normal. This uneven, spiky signature is called a spectral power distribution, and it's the reason 2 lights that both look roughly white to a casual glance can render the exact same red sweater as 2 noticeably different shades of red. This is also why screens and paint behave so differently from each other, even though both are, in the end, just manipulating light. A screen works by addition. Every pixel is really 3 tiny lights, red, green, and blue, and by adjusting how brightly each one glows, the screen can trick your 3 cone types into registering almost any color at all, including white, produced by switching on all 3 lights together at once. Paint and ink work by subtraction instead. A pigment doesn't add color to light, it removes wavelengths from it, absorbing some and reflecting the rest. Mixing pigments together doesn't combine their glow, it combines their appetite for absorption, which is why mixing paints tends to move you toward darker, muddier colors rather than brighter ones, and why printers typically rely on cyan, magenta, and yellow inks, along with a separate black, rather than the red, green, and blue of a screen. Not everyone's eyes sample this spectrum the same way. A meaningful percentage of people, most commonly men, carry a genetic variation affecting one of their three cone pigments, most often the ones tuned to red or green, resulting in some degree of red-green color vision difference. This isn't a flaw or a broken version of normal sight. It's a genuinely different biological sampling of the very same physical spectrum, one where certain colors that look clearly distinct to most people can appear far more similar, or even identical, to someone with this variation. Color, in the end, has never been a fixed property sitting quietly inside the world, waiting to be discovered. It's something built, moment to moment, through a specific and sometimes quite variable partnership between light, matter, and a particular nervous system doing the interpreting. Let's step outside for a moment, at least in our imagination, and look up. The atmosphere is almost perfectly transparent, and yet it manages to paint the sky a different color every few hours, without ever adding a single drop of pigment to the air. During the day, the sky glows blue. Near sunset, that same sun can turn buttery yellow, then deep orange, then a smoldering red. This entire performance comes down to something called scattering, and specifically a type named after the physicist Lord Rayleigh, who worked out that molecules far smaller than the wavelength of light, the nitrogen and oxygen that make up most of our air, scatter shorter wavelengths far more strongly than longer ones. Blue light gets knocked around and redirected across the sky many times more than red light does. So when you look up, away from the sun, on an ordinary afternoon, you're not looking at some blue ceiling stretched overhead. You are looking at scattered sunlight, arriving at your eyes from every direction of the sky at once, mostly blue because blue is what got bounced around the most. You might reasonably ask why the sky isn't violet instead, since violet light has an even shorter wavelength and gets scattered even more strongly than blue. A few things conspire here. The sun simply emits less violet light to begin with. Some of what little violet there is gets absorbed high in the atmosphere before it ever reaches you. And your own eyes are less sensitive to violet than to blue in the first place. All of these small effects add up, and blue wins out as the color your brain settles on. Near sunrise and sunset, the geometry changes completely. When the sun sits low near the horizon, its light has to travel through a much thicker slice of atmosphere to reach you, far more air than when the sun is directly overhead. Along that longer path, nearly all the blue and green light gets scattered away before it arrives, leaving mostly the oranges and reds to survive the journey and reach your eyes directly. That's why sunsets burn warm, and why the effect grows even more dramatic when there's extra dust, smoke, or pollution in the air, since larger particles scatter a broader range of wavelengths and can deepen a sunset into something almost otherworldly. Rain gives the sky its most theatrical trick of all, the rainbow. Sunlight enters a spherical raindrop, bends as it crosses the surface, bounces once off the inside back wall of the droplet, and bends again as it exits. Because water bends different wavelengths by slightly different amounts, red light and violet light leave the droplet at very slightly different angles, and your eye ends up catching red from one group of droplets and violet from another, with the whole spectrum arranged neatly in between. This is why a rainbow always appears directly opposite the sun from where you're standing, and why you have to have the sun at your back to see one at all. Sometimes a fainter second rainbow appears further out, formed by light that bounced twice inside the droplet instead of once, and its colors run in reverse order, red on the inside this time instead of the outside. Between the two bows, there's often a visibly darker band of sky, a genuine, physical dimming, not a trick of the eye, sometimes called Alexander's dark band, after the philosopher who first described it. almost 2,000 years ago. Clouds work by an entirely different kind of scattering. Rayleigh scattering, the kind responsible for the blue sky, only works cleanly when the scattering particles are much smaller than the wavelength of light, which is true for individual gas molecules, but not for water droplets. Cloud droplets are far larger, closer in size to the wavelength of visible light itself, or bigger, and this calls for a broader description worked out by the German physicist Gustav Mie. Mie scattering doesn't favor short wavelengths nearly as strongly as Rayleigh scattering does. It redirects red, green, and blue light in roughly equal measure, and that even mixture is exactly why a healthy, sunlit cloud looks bright white rather than blue. Thicker clouds, where light has to bounce through many droplets before finally escaping, lose more of that light to repeated scattering along the way, and tend to look gray rather than white, simply because less total light manages to make it all the way through to your eyes. Haze and smog work through this same Mie process, larger aerosol particles scattering a broad mixture of wavelengths and gently whitening the whole sky, softening colors and washing out the crisp blue you'd otherwise see on a perfectly clean day. The atmosphere is, in a very real sense, a planet-sized optics laboratory running quietly overhead every single day. Air molecules scatter blue light into the daytime sky. Dust and haze scatter a broader mix of colors and whiten the horizon. Water droplets sort sunlight into rainbows. And thin ice crystals and cirrus clouds can bend sunlight into faint glowing rings and bright side patches called sundogs. None of it is decoration painted onto the world. Every color above you is a direct, visible record of electromagnetic radiation colliding, again and again, with the ordinary matter of the sky. Let's pause here for just a moment. If your mind has started to drift a little, that's exactly right. That's exactly what this is for. There's no need to hold on to every detail. Just let the ideas settle over you the way light settles over a room in the evening, quietly, without asking for your attention. We still have a little further to go tonight, from the sky outside, down into the eye that's been quietly catching all of it, and finally, into the strange, flickering heart of the light itself. You don't have to stay for all of it. Your body will know what to do. All of this light, scattered and bent and colored by the sky and the world, has to end its journey somewhere. And for you, that somewhere is your own eye. Light first crosses the cornea, the clear curved dome at the very front of the eye, which does most of the actual bending or focusing, simply because light changes speed as it moves from air into that dense, living tissue. It then passes through a clear fluid, through the pupil, that dark opening at the center of the iris, which widens in dim light to let more in and narrows in bright light to protect what's behind it. The pupil isn't actually black, by the way. It only looks that way because almost all the light entering it gets absorbed deep inside the eye rather than bouncing back out toward you. Behind the pupil sits the lens, which fine-tunes the focus that the cornea has already mostly set up, flexing rounder to focus on something close, flattening out to focus on something far away. Finally, light reaches the retina, a thin sheet of neural tissue lining the back of the eyeball, where the actual detection happens. Interestingly, the image that forms there is upside down and flipped left to right. Your brain doesn't need to physically rotate this image the way you might rotate a printed photograph. It simply learns, from birth, that up in the retinal image corresponds to a certain pattern of neural signals, and it never needed a right-side-up picture in the first place. There's no tiny person sitting inside your skull, staring at a little screen, waiting for someone to flip it over. The retina holds two main kinds of photoreceptor cells, rods, which are extremely sensitive and handle low-light vision, but can't distinguish color, and cones, which need brighter light, but deliver sharp detail and full color. You have roughly 120 million rods and around 6 million cones, and they aren't spread evenly. Cones are packed densely into a small central region called the fovea, which is why you get your sharpest, most colorful vision only in the very center of your gaze, while everything at the edges stays a little blurrier and less colorful than you probably assume. Rods, meanwhile, are almost entirely absent from that central fovea and grow more common toward the edges of your vision, which is why, on a clear night, a faint star sometimes seems to vanish the instant you look directly at it, only to reappear the moment you glance slightly to one side. You're not imagining it. You're simply shifting that star's light off your cone-rich center and onto your rod-rich periphery, where faint light is easier to catch. There's one more small quirk of the retina worth sitting with. At the exact spot where the optic nerve gathers itself together and exits the back of the eye, carrying all of this visual information toward the brain, there simply isn't room for any photoreceptors at all. This creates a genuine blind spot in each eye, a small region where you are, quite literally, not seeing anything. You've never noticed a gap floating in your vision, and you never will, because your brain quietly fills that missing patch in using the surrounding visual pattern, and because your other eye is almost always covering that same piece of the world from a slightly different angle. It's a strange, almost humbling fact. Your brain has been discreetly editing your entire visual experience, seamlessly patching over a real, physical hole in your vision every single moment for your entire life, and you've simply never been given a reason to suspect it. Inside each photoreceptor sits a light-sensitive pigment. When a photon strikes it, the pigment's molecular shape changes, triggering a cascade of chemical signals that eventually becomes an electrical impulse. And here's a small, satisfying twist. In complete darkness, your photoreceptors are actually active, constantly signaling. Light doesn't turn them on, it turns them down. Vision, at its most basic chemical level, works by light interrupting a baseline of ongoing activity, not by switching something on from nothing. Before any of this information ever leaves the eye, it's already being processed, compared, and organized by layers of specialized cells inside the retina itself, cells that sharpen edges, detect motion, and compress raw brightness into something more useful. What travels up the optic nerve toward the brain isn't a simple, untouched picture. It's already been edited. From there, signals cross at a structure called the optic chiasm, arriving at the visual cortex at the back of your brain, where they're distributed across a whole network of specialized regions responsible for color, motion, depth, and shape, all working in parallel, all stitching themselves back together into the single, seamless, continuous world you experience without ever noticing the astonishing machinery underneath it. There's a further, slower kind of adjustment worth mentioning, one you've almost certainly felt without ever knowing its name. Walk from bright daylight into a dim room, and for the first minute or two, you can barely see anything at all. Slowly, gradually, over something like 20 to 30 minutes, your night vision keeps improving, long after your pupils have already finished widening. Most of that ongoing improvement doesn't come from the pupil at all. It comes from a slow chemical process inside the rods themselves, rebuilding a light-sensitive pigment called rhodopsin, which gets partially used up, or bleached, by bright light and takes real time to regenerate in the dark. This is called dark adaptation, and it's part of why stepping outside for a smoke break or checking your phone in bed can quietly reset your night vision back to nearly zero, forcing your eyes to slowly rebuild their sensitivity to darkness all over again. The eye is often compared to a camera, and the comparison is useful up to a point. The pupil resembles an aperture, The lens focuses light. The retina behaves loosely like a sensor. But the comparison breaks down quickly under real scrutiny. A camera captures one still frame at a fixed exposure. Your eye is never still. It's constantly moving in tiny, rapid jumps called saccades, constantly refocusing, constantly adjusting its aperture, and crucially, it begins interpreting and compressing the image before that information has even left the eyeball, long before it reaches anything resembling a brain. And like any real optical instrument, your eyes aren't perfect. The curvature of the cornea and lens can introduce subtle distortions, and because different wavelengths bend by very slightly different amounts, even a healthy eye can suffer a faint version of chromatic aberration, the same effect that gives cheap camera lenses their telltale colored fringing around high-contrast edges, usually far too subtle for you to consciously notice, but there, quietly, in the background of every single thing you've ever looked at. And color perception itself carries one final, quietly beautiful complication. Your brain doesn't just register the raw wavelengths hitting your eye. It compares them constantly to their surroundings, correcting for the color of the ambient light so that a white sheet of paper still looks approximately white whether you're reading it under a warm lamp or cold daylight, even though the actual wavelengths reaching your eye are wildly different in each case. This is called color constancy, and it's one of the many small miracles your visual system performs every waking moment, entirely without asking for your permission or your attention. Let's return now to that paradox we opened with tonight, because it's time to build it properly, piece by piece, starting with the wave side of the story. Long before Young's experiment, the Dutch physicist Christian Huygens had already proposed a beautifully simple way to picture how a wave moves through space at all. Imagine every point along an advancing wavefront as its own tiny source, sending out its own small spreading ripple. Add up all those countless small ripples together, and their combined edge becomes the next wavefront, moving steadily forward. This simple, almost childlike picture turned out to explain something that had puzzled people for a long time. Why light seems to spread out slightly whenever it squeezes through a narrow gap, rather than casting a perfectly crisp-edged beam straight through. That spreading and bending around edges, called diffraction, produced one of the most delightfully embarrassing episodes in the entire history of physics. In the early 1800s, the French physicist Augustin-Jean Fresnel had built an increasingly precise mathematical theory of how light waves diffract around obstacles. A physicist named Simeon Poisson, reviewing Fresnel's work for a scientific committee, worked through the equations and found something he considered so obviously ridiculous that he offered it as proof the whole wave theory had to be wrong. The mathematics predicted that if you shone a beam of light at a small, perfectly round opaque disk, there should be a single bright spot glowing at the very center of the disk's shadow, exactly where you'd expect the deepest darkness to be. Poisson meant this as a takedown. Another physicist, Francois Arago, decided to actually go and check. He set up the experiment, aimed a beam of light at a small round obstacle, and looked directly into the heart of its shadow. There, exactly as the despised equations had predicted, sat a single small, stubborn point of light. An objection built to destroy the wave theory of light instead became one of its most famous and celebrated confirmations, and today it's remembered, with a certain fondness, as the Poisson spot, or sometimes, a little more generously, the Arago spot. By the early 1800s, the English scientist Thomas Young ran an experiment so simple in design and so strange in outcome that it's still taught in physics classrooms exactly as he first performed it. He shone light through two narrow, closely spaced slits cut into an otherwise opaque screen and let it fall onto a wall beyond. If light were simply a stream of tiny particles, you'd expect two bright stripes on the far wall, one behind each slit. That is not what he saw. Instead, he found an entire series of alternating bright and dark bands, stripe after stripe after stripe, a pattern that only makes sense if you assume light is spreading outward from each slit as a wave, and that those two waves are overlapping and interfering with each other on the far wall. Where two wave crests arrive in step, they reinforce each other and the light grows brighter. Where a crest from one slit arrives exactly alongside a trough from the other, they cancel each other out entirely, leaving a dark band, even though light is arriving there from both openings. Young had produced direct, visible proof that light behaves like a wave. This bending and spreading, called diffraction, shows up whenever light squeezes through an opening or slides past an edge roughly comparable in size to its own wavelength. It's subtle for visible light, since visible wavelengths are only a few hundred nanometers long, far smaller than almost anything you encounter in daily life, but it's never entirely absent. Even a perfectly made lens, focusing light from a single point, can't produce an infinitely small, perfectly sharp dot. It produces a small bright disk surrounded by faint rings, called an Airy pattern, and this sets a hard, unavoidable limit on how much fine detail any telescope, microscope, or camera lens can ever resolve, no matter how expensive or well-engineered it might be. There's also polarization to consider, one more piece of proof for the wave picture. In an ordinary beam of light, the oscillating electric field wobbles in every possible direction as it travels. A polarizing filter is like a narrow picket fence for light, only letting through the component of the wave that's oscillating in one particular direction. This is the entire principle behind polarized sunglasses, which cut down glare by blocking the strongly polarized reflections that bounce off flat surfaces like water or wet pavement. And it's also, in a very different application, the underlying trick behind how liquid crystal displays control brightness pixel by pixel across your phone or your television. Some animals put this same physical property to far more practical use than we do. Certain bees and other insects can directly sense the pattern of polarization scattered across the sky, invisible to us entirely without special equipment, and use that pattern as a built-in compass, reading the angle of scattered sunlight to navigate home even on a cloudy day, when the sun itself might not be visible at all. It's a quiet reminder that the world holds entire channels of information running past us constantly, fully real, fully physical, simply outside the narrow window our own particular eyes happen to be built to notice. And then there's the shimmering, shifting rainbow you sometimes see in a soap bubble or a thin film of oil on a wet road. That's interference again, but this time from light bouncing off the very front and the very back surface of an extremely thin layer, two reflected waves recombining, some wavelengths reinforcing, others canceling, and as the thickness of the film shifts by even a fraction of a wavelength, the pattern of colors flows and drifts across the surface like something almost alive. By the close of the 19th century, this wave picture of light seemed essentially complete and triumphant. Interference, diffraction, and polarization had all been beautifully explained. James Clerk Maxwell had unified light with electricity and magnetism into a single elegant framework. Physics, for a brief and confident moment, seemed nearly finished. Then one stubborn little problem refused to go away. Physicists were trying to understand something that seemed, on paper, like it should be simple: the light given off by a hot, glowing object. Classical wave theory made a prediction, and it was a genuinely absurd one. It suggested that as wavelengths got shorter and shorter, a hot object should radiate more and more energy, without limit, rising forever into the ultraviolet and beyond. This became known, only half-jokingly, as the ultraviolet catastrophe. Real glowing objects, of course, were not exploding with infinite energy. Ovens did not incinerate kitchens. Fireplaces did not blind their audiences. The catastrophe existed only in the mathematics. Somewhere, the theory itself had gone quietly, badly wrong. In 1900, the German physicist Max Planck found a fix, though at first he treated it more as a convenient mathematical trick than a deep truth about nature. He proposed that matter could only emit or absorb light in specific, discrete chunks, which he called quanta, rather than in any smooth, continuous amount. The size of each chunk depended directly on its frequency. Higher frequency light came only in larger packets. Lower frequency light came only in smaller ones. This single restriction, quietly and elegantly, made the ultraviolet catastrophe disappear from the math entirely, matching the real, observed behavior of glowing objects with remarkable precision. 5 years later, Albert Einstein pushed this idea much further and much more boldly to explain a separate, puzzling observation called the photoelectric effect. When light shines on certain metal surfaces, it can knock electrons loose. Classical wave theory predicted that brighter light, carrying more total energy, should always be able to knock electrons free eventually, given enough time, no matter its color. Experiments showed something stranger. Below a certain threshold frequency, no amount of brightness, however intense, would release a single electron. Above that threshold, even very faint light could knock electrons free almost instantly. Einstein proposed that light itself doesn't just arrive in a smooth, continuous wave. It arrives in individual, localized packets of energy, later named photons, and each one either carries enough energy to free an electron, or it doesn't, regardless of how many other photons happen to be arriving alongside it. It's a little like trying to pay a fixed entrance fee using envelopes of cash. If each individual envelope contains less money than the fee requires, it doesn't matter how many thousands of envelopes you send. None of them, alone, can unlock the door. This single insight, not relativity, which came the very same year, and not general relativity, which came a decade later, is specifically what earned Einstein his Nobel Prize. It's also, quietly, the exact physical principle running underneath a solar panel and inside the sensor of every digital camera. A solar cell is essentially a carefully engineered version of that same photoelectric interaction, tuned so that incoming photons reliably knock electrons loose and herd them into a usable electrical current, rather than letting that energy simply dissipate as heat. Every photograph you have ever taken on a phone worked the same basic way. Countless individual photons striking a grid of tiny light-sensitive sensors, each one releasing a small measurable signal, together assembling, one discrete quantum event at a time, into a picture that looks perfectly smooth and continuous once you step back and view the whole. Further proof came from the American physicist Arthur Compton in the 1920s, who fired X-rays at electrons and found that the scattered X-rays came back with a longer wavelength than they went in with. Exactly as you'd expect if you treated the whole interaction as a literal, physical collision between a photon and an electron, with momentum being exchanged between them, the same way two billiard balls exchange momentum on a table. This confirmed, beyond doubt, that photons carry real, physical momentum despite having absolutely no mass. That momentum, tiny as it usually is, has real consequences. Sunlight pushes gently but constantly on everything it touches, on dust drifting through the solar system, on the tenuous outer wisps of a comet's tail, always pointing it subtly away from the sun regardless of which direction the comet itself happens to be traveling. And on carefully designed spacecraft called solar sails, thin, mirror-bright sheets built specifically to catch this gentle push and slowly, patiently accelerate outward using nothing but sunlight itself. No fuel required at all. The force involved is almost absurdly small, but space offers something in endless supply that a rocket engine never can: uninterrupted time. Given years instead of minutes, even the faintest possible push can add up into something genuinely useful. On a much smaller scale, tightly focused laser beams can generate enough concentrated force to trap and gently move individual microscopic particles, even single living cells, a technique called optical tweezers, developed extensively by the physicist Arthur Ashkin, work that quietly earned him a Nobel Prize decades after he first began. So now we have both stories confirmed. Light spreads and interferes like a wave, and light exchanges its energy in discrete, particle-like packets. And the experiment that shows both of these facts colliding head-on, in the most vivid way physics has ever produced, is Young's double-slit experiment again, run one more time, but now with the light turned down so low that only a single photon passes through the apparatus at a time. Here is what happens. Each individual photon arrives at the detector as one single, localized dot. Not a smear, not a faint wave spread out gently across the whole screen. One dot, at one specific location, exactly like you'd expect from a particle. And yet, if you let this experiment run for a long time, sending photons through one at a time, minutes apart, hours apart, and you slowly build up a picture of where each individual has landed, the accumulated pattern is unmistakably the same interference pattern you'd get from waves passing through both slits simultaneously. The bright bands and dark bands reappear, stripe by stripe, built up one lonely photon at a time. There is no ordinary explanation for this. Each individual photon, somehow, behaves as though it is aware of both slits at once, even though it will only ever be recorded arriving at one single point. Quantum theory handles this using something called a probability amplitude, a mathematical object that isn't quite the same thing as an ordinary probability. It carries both a magnitude and something called a phase, and these amplitudes can be added together, the way you might add two waves, before you ever calculate the actual chance of detecting something at any given spot. Where the amplitudes for passing through slit 1 and slit 2 reinforce each other, detection there becomes likely. Where they cancel, detection there becomes essentially impossible. The interference isn't happening between different photons colliding with each other. Remember, they're arriving minutes apart, entirely alone. The interference is happening within the mathematics describing a single photon's own possibilities. And here's the part that tends to keep people awake at night, ironically, on a channel meant to help you sleep. If you modify the experiment to somehow detect, even in principle, which slit each individual photon actually passed through, the interference pattern vanishes completely, instantly, replaced by two simple, ordinary bands, exactly what you'd expect from particles behaving like tiny, sensible little marbles. Simply having the potential for which path information to exist, whether or not anyone ever consciously looks at it, is enough to erase the interference. This isn't about awareness or observation in any mystical sense. It's about physical information becoming, even in principle, available somewhere in the universe. When that path information exists, the delicate phase relationship required for interference gets scattered and lost into the wider environment, a process physicists call decoherence. So what, in the end, is a photon actually made of? Modern physics gives an answer that's honestly a little more austere and elegant than either wave or particle on its own. The electromagnetic field itself is treated as fundamental, stretching invisibly through the whole of space, everywhere, all the time. A photon isn't a tiny object placed inside that field. A photon is a single, quantized ripple of that field, a specific, discrete unit of energy, momentum, and oscillation. It has no rest mass, no fixed outer edge, no definite little boundary marking where photon ends and empty space begins. It's not a wave in the everyday sense, and it's not a particle in the everyday sense. It's something genuinely new, something our language, built entirely from everyday, human-scale experience with balls and ripples and streams, was simply never designed to describe cleanly. Wave and particle were never rival, competing identities that light kept switching between. They were always just two limited, human-scale shadows, cast by something deeper, something quantum, that never needed to choose between them in the first place. The theory that describes all of this precisely, mathematically, is called quantum electrodynamics, developed independently by Richard Feynman, Julian Schwinger, and Shinichiro Tominaga, work that eventually earned all three a shared Nobel Prize. It's widely regarded as one of the most accurate theories human beings have ever produced, capable of predicting certain properties of the electron to a precision matching experiment to somewhere around 10 decimal places. Feynman helped popularize a visual shorthand for organizing its calculations, now called Feynman diagrams, simple sketches of lines and vertices representing electrons and photons meeting, interacting, and scattering. It's worth being careful with these diagrams, though. They're brilliant bookkeeping tools for organizing a calculation, not literal miniature films of tiny objects flying through space along visible little tracks. Buried inside these calculations is a strange character called the virtual photon. Physicists often describe the electric force between two charged particles as arising from an exchange of virtual photons passing between them. And while that's a genuinely useful way to organize the mathematics, it isn't quite the same as saying two charges are literally, constantly lobbing detectable flashes of light back and forth. A virtual photon is a feature of the calculation, not a hidden little courier waiting to be caught on camera. Photons also carry a quantum property called spin, and for a particle with no mass and no size, this needs its own careful translation. It doesn't mean a tiny sphere physically spinning on an axis the way a planet spins. For a photon traveling freely through space, this property shows up as something called helicity, essentially a fixed relationship between its angular momentum and its direction of travel, and it comes in exactly two possible states, closely tied to the two directions a beam of light can be circularly polarized. Photons also belong to a broad family of particles called bosons, which have an unusual and rather sociable property. Unlike electrons, which stubbornly refuse to share the exact same quantum state as one another, huge numbers of photons can pile into the very same state together, all in step, all moving the same way. This shared, cooperative behavior is precisely what makes a laser possible in the first place. Countless photons marching forward together in near-perfect unison. Even the seemingly perfect emptiness of a vacuum turns out not to be entirely empty. Quantum field theory assigns even the total absence of light a lowest possible energy state, and that state still carries a faint, irreducible flicker of uncertainty, sometimes loosely described as vacuum fluctuations. It's tempting and very common in popular science writing to picture this as a chaotic swarm of tiny particles constantly blinking into existence and instantly vanishing again, but that image is usually more theatrical than accurate. It's better understood as a description of the underlying uncertainty woven into the quantum field itself, an uncertainty with genuine, measurable consequences in carefully designed laboratory experiments, but not literally a hidden crowd of particles briefly breaking the rules when nobody's looking. Every one of these quantum ideas eventually adds back up into the perfectly ordinary, classical waves of light you already know: radio waves, laser beams, sunlight streaming through a window. When enormous numbers of photons occupy what's called a coherent state, their combined behavior reproduces a smooth, continuous, classical electromagnetic wave with extraordinary accuracy. The classical wave picture was never wrong. It's simply what an enormous crowd of quantum events looks like from far enough away that the individual events blur together into something smooth. These quantum properties of light aren't only philosophically interesting, either. They've become genuinely practical. Modern research uses individual photons for quantum cryptography, a method of sending information in a way that reveals, almost automatically, whether anyone has secretly tried to intercept it along the way, since the very act of measuring a quantum state tends to disturb it. Related techniques allow something called quantum teleportation, transferring the exact quantum state of one particle onto another distant particle, using a combination of entanglement and ordinary classical communication. Despite the dramatic name, nothing physical or material is actually beamed anywhere. No person, no object, not even the original particle itself, is ever transported. Only a very specific, delicate pattern of quantum information moves, and even that cannot travel faster than the speed of light allows. Light is also being pressed into extraordinary new service far beyond ordinary lenses and mirrors. Engineered materials called metamaterials, built from structures far smaller than the wavelengths they're designed to manipulate, can bend and focus light in ways no naturally occurring material ever could, though the more sensational old claims about effortless invisibility cloaks have generally traveled a fair bit further than the actual laboratory results. Optical clocks now measure time using the extraordinarily stable, precise frequencies of light emitted by individual atoms, so precise that two such clocks placed at only slightly different heights above the ground can measure the tiny difference in how gravity itself is stretching time between them. And in perhaps the most dramatic recent triumph of all, in 2015, an instrument called LIGO used two long, perpendicular arms and extraordinarily sensitive laser beams to directly detect gravitational waves for the very first time. Ripples in the fabric of space-time itself, set loose by two black holes colliding more than 1 billion years ago, stretching and squeezing one arm of the detector relative to the other by a distance far smaller than the width of a single proton. Light, in that experiment, wasn't just being observed. It was being used as the most sensitive ruler human beings have ever built to measure a disturbance in the fabric of reality itself. There's one more thread of this mystery worth pulling on tonight, gently, before we let it rest. It concerns something Einstein himself found deeply uncomfortable, a phenomenon he once dismissively called spooky action at a distance. Under certain conditions, often inside a special crystal that splits one incoming photon into two lower energy photons at once, those two new photons can be produced together in a way that links their properties so intimately that measuring one instantly tells you something certain about the other, no matter how far apart they later travel. Before either photon is measured, quantum theory doesn't describe them as each secretly possessing some fixed, hidden polarization waiting quietly to be discovered, the way a sealed envelope already contains a specific, fixed letter before you open it. It describes them as existing in a shared, undivided quantum state, a genuine superposition of possibilities, right up until the instant either one is actually measured. Send one photon to a lab on one side of a country, and its entangled partner to a lab on the other side, and measuring one immediately correlates with the outcome of measuring the other, in a way that no simple, ordinary explanation involving hidden, pre-agreed instructions can account for. The physicist John Bell proved mathematically, in the 1960s, that any theory relying on the photons secretly carrying predetermined, local instructions from the very start could not reproduce the strength of correlations that quantum mechanics actually predicts. Decades of increasingly careful experiments by physicists including John Clauser, Alain Aspect, and Anton Zeilinger, work that eventually earned a Nobel Prize, have confirmed those quantum predictions again and again, ruling out that simpler, more comforting explanation. And yet, importantly, this strange connection cannot be used to send an actual message faster than light. Each individual measurement, on its own, still looks completely random. The correlation only becomes visible once someone compares results from both locations afterward, through perfectly ordinary, light-speed limited communication. Nature, it seems, has found a way to be strange without ever breaking its own most fundamental rule. So where does that leave us? At the end of a very long night, spent chasing something that touches your eyes every waking second of your life. Light turns out to work through several different layers, each one true, each one necessary, none of them complete on its own. Electromagnetic theory explains how it propagates through space as a wave. Relativity explains why its speed never changes and how it links space and time together into one continuous fabric. Quantum theory explains how it's born and how it's finally caught, one discrete photon at a time. None of these are competing stories fighting for the same throne. They are different windows onto the exact same underlying reality, each one clearest at its own particular scale. Light has already told us the age of the universe, the composition of stars we will never visit, and the existence of gravitational waves rippling through space-time itself. It may yet reveal what dark matter actually is, or how gravity itself fits into the quantum world. Its remaining mysteries are not a sign of failure. They are simply the edge of an extraordinary map, still quietly being drawn, one photon at a time, by one of nature's oldest and most patient messengers. Think back to where we started tonight, with that opening paradox, wave or particle. By now, hopefully, the question itself has started to soften. It was never really a choice between two rival identities. It was always a single, deeper thing, expressing itself differently depending on how closely and in what way we happen to be looking. A ray is simply what light looks like when wavelength barely matters. A wave is what it looks like when interference and bending take center stage. A photon is what it looks like the instant it's finally caught. None of these are masks light wears and discards. They're simply the different angles from which a single, deeper truth becomes visible, the way a single mountain looks entirely different from its northern slope than from its southern one, without ever once being two separate mountains. And here is the last thought I want to leave you with, the mirror I promised at the beginning of tonight. Every single thing you have ever loved, every face, every sunset, every quiet room at the end of a long day, has reached you only because light was willing to cross an unimaginable distance, bend around obstacles, scatter through an atmosphere, and finally, gently, land on the back of your eye. You have spent your entire life catching photons that started their journey long before this moment, some of them long before you were even born. And somewhere, tonight, wherever you are, more of that ancient light is still arriving, quietly, patiently, asking nothing of you but to be received. There's nothing left to figure out tonight. No equation to hold on to. no name to remember, no law to recite in the morning. All of it can simply drift now, the way it wants to, the way your own eyes are probably already drifting. Let the sky be blue without needing to explain why. Let the stars be old without needing to count the years. Let the light finish its long, quiet journey, exactly the way it always does, and let yourself finish yours, right here, right now. If tonight helped your mind grow quiet, consider subscribing to Somniora Mind, or leaving a comment to let me know where in the world you're listening from, or simply tapping like on your way out. It helps more than you'd think, and it costs you nothing but a moment before you close your eyes. Rest now. You've earned it. Good night.